So we got experiment 4. This is year 2015. Who knows if that changes in the future as far as the number. But we're definitely doing this particular reaction where we're oxidizing butanol to butanal. And that is the agent that we're supposed to be using. So let's start with our IRs and NMRs. So we have some starting material. And as typical, this is where we have a spectra of butanol from the bottle. So we get a little bit of a look here. So there it is. It's pretty obvious. You're getting used to this. How many functional groups do we have present? You have alkane and you have an alcohol. So once you locate the two functional groups, you should go to Pavia and look up under alkanes for how you can pick. They've got 3 or 4 reference spectra that you can see how they have picked their spectra. But in any event, for the carbon sp3 with a hydrogen on it stretching. So yet again, that 3000 mark is very important. Anything just to the right, so you can see all of this right here, is obviously your alkane, which is your carbon sp3 with a hydrogen stretch. As far as alkane is concerned, yet again, we're back to looking in this region. Some of these absorptions right here are related to the CH bend. How many of them are associated with an aldehyde, like some of these, I don't know for sure. Arguably, because there's no aromatic, you could probably circle this and call it a CH bend, and that would be fine. Moving on to the alcohol, again, we should probably go to Pavia really quick, have a look. So if you look up in the alcohol section, you can see the black box, you can see some representative spectra where they label it for you. There's one reference, there's 2 more. The more important part though, I mean, I think by now most of us know that this big OH stretch peak, and it means hydrogen bonded because it's very broad. If you go to NIST website and look at a gas phase, all it means is you don't have as much hydrogen bonding. In a gas phase, this peak would be a sharp spike. You can see that easily on NIST. This is the chart that's going to tell us a little bit about, more importantly, the CO stretch. So when you talk about primary, secondary, and tertiary alcohols, you can see primary, it's at 1050. Ours is primary. Secondary should be 1100-ish. So we're expecting to see a CO stretch in that vicinity. So you go back here, and we can see we have an absorption, a strong one at 1072. And what's interesting, we have a couple more spikes here. Often, just like menthol when we started, you can get 2 absorptions. One is symmetric, one is asymmetric. I don't know which is which. Long story short, you could at least circle this and say it's a CO stretch of this alcohol. Other than that, I really don't see any reason to circle much else to say that we're 100% confident. Our product, which is the aldehyde, now I managed to get one of these right out of the bottle, butanal. So obviously here you have alkane, right, functional group, but you also have an aldehyde. So let's go to the aldehyde section. It's always nice to look in Pavia for some examples first. So there's the aldehyde section. Here's the list of things that you might circle. And then when you start looking at the reference spectra, it's interesting that as far as the aldehyde is concerned, in this particular example, all these circles is the CO stretch. And you can make out what's going to be called the Fermi doublet. And down here, they're telling us, let's take a look. You're going to see that the hydrogen on the carbon of the aldehyde, it has 2 weak bands, one around 2800-ish, the other at 2700-ish. They're saying pair of weak bands. But the only way you're going to make sense of this is to look at their reference here. Notice how one of them right there is at 2700, and see that tiny little blip right there. They're pointing at it, and you can see that the CH sp3 stretch is so strong that it's kind of overwhelming that 2800 one of this. So you don't see a clear Fermi doublet, is what we used to call it. So let's look down here at another one. Now notice how in this one, the sp3ch stretch is very, very small. So you can clearly see the 2 peaks of the Fermi doublet that they're referring to. And if we go down and look here, you have no sp3 carbons. So obviously these 2 peaks are very isolated and easy to see. Something tells me that our product is going to look a lot like this, where you may or may not see the one, right? The other one could be buried. They often talk about a CO overtone. When you see a little spike, that is the overtone of the CO stretch. And you can see here they didn't label it, but the little spike is there. Little spike is still there. So when you see it, you kind of know it and you can circle it. So let's look at ours. And it is going to turn out almost exactly like the one that was in Pavia. So there is obviously your CO stretch, right? 1727. And then right there, 2877, 2938, and 2963. That's your alkane carbon H stretch, sp3 carbon. This one, you know, this is sort of broad enough. It's not the nice characteristic, very sharp spike. Probably is the overtone with a touch of water, something like that in there. Now going back to the CH stretch where you're looking for the 2, this one that I did, you can clearly see the 2 right there. So you can circle those 2 and call it the CH stretch of the aldehyde. Some of you, your alkane might be so broad you're going to bury that second one there, but I think you get the drift. Other than that, I really have no intention of circling anything else, but again, because all you have is alkane and aldehyde, this one you could arguably circle this because there's nothing really else there. You could say it's a CH bend. So that takes care of the IR. Now we'll move on to the NMR. So I'm going to start off with, I have a reference spectra. This came right out of the jar and it was run on our instrument. So butanol, that's the character right there. And you can see clear as day, we have we have TMS right there at 0, quite a bit that day. What we can make out pretty clear is the CH2 group next to the OH. That should be the signal furthest to the left. And it's an ugly kind of looking triplet. It's not a pretty one, but when you integrate this, you can see how it comes to 2, right? This one turns out, as sharp as it turns out to be the hydrogen on the oxygen. And folks, when this is run, depending on the concentration of it, this thing is quite variable. Some days it's a broad thing. It could be over here, it could be over here. But in this particular day, it came out nice and sharp, and see the integral's 1. Then you have this blob. It's a forest of peaks, and that comes out to 4.3. That's 2. So this is going to end up being 4. What you're going to see there is the 2 CH2 groups here are bundled up in there, and this remaining blob, which is close to being 3.4. That's essentially the methyl group. The reason why this is so broad is because some of the coupling that's taking place between one and the next door neighbor is not exactly the same as the other neighbor. And that's why you're not getting a nice N+1 peak. But you can make out from the integration, this is butanol. Key peak we're going to look at is right there at 3.6-ish, right there in our product. This is the reference material of the product we intend to get. So this is pure, came straight out of the bottle. So way down at almost at 10, you can clearly see how you have the aldehyde peak. One thing I want to stress though, folks, do you see the phasing? Do you see how the baseline is here? And there's a little bit of it dips down there. Whenever that phasing of this peak, it's slanted a little too far this way, in this case it's slanted like this way, that integration you can't necessarily trust it. So it's no surprise that even though we're setting this to be 1, the area under it, the ones over here are not going to work out that great because their phasing is not the same as this. So just to let you know, you don't have to panic, and clear the fact that that's a little triplet. All it means is that hydrogen, and it's normal, because you have an sp2 carbon there, it's actually talking to these 2. So it sees these 2, does a little bit of splitting. This will be a triplet. And that also means that these 2 have to be talking back to this 1. So these are going to talk to these at a coupling of, say, 7, but it's going to talk to these at a coupling of maybe 3. So the way this is talking to one neighbor and the other, not going to be identical, so it's not going to be a pretty looking signal. However, that signal right there, as far as this is concerned, the CH2, should be furthest left in this region. So there we go. There's what looks like a triplet with extra splitting, right? The integration is 2, and it is what we thought, the CH2 next to the carbonyl. So it's further, and this one's only coming out, what, 2.3 or something like that? Now remember, butanol, the starting material, was 3.6 or 7? So obviously, if you had any residual butanol, it's going to be sitting, here's 3, right over here in our product. This here, it's relatively symmetrical and nice. It comes out to an integration of 2.6. That's another CH2. It's that CH2 Let's see if this is going to focus. There we go. It's going to be the CH2 next to the end, and then the methyl group. It's not going to be a really nice looking triplet, but you can make it out here, and that integration is going to come out to roughly 3. So this is butanal, the product pure out of the jar. So let's go ahead and look at the carbons real quick. Here is the butanol, and as you'd expect, there should be four carbon signals. Flat baseline, nothing, nothing, nothing. Obviously, the signal that's furthest left has to be the carbon next to the alcohol, and then the next one, and then the next, and the next. So there's only 4. I'm pretty sure you can find this on that Japanese SDBS site. I'm pretty sure it's already assigned for you. This is the product. We expect to see something down near 200. Sure enough, we do. That's your carbonyl carbon. All that's left should be 3. You see one just below 50, and then 2 more. And it will follow in succession, right? So the one that's at 46-ish is this one. And then as you're heading right, it'll be that CH2, then the CH3. And that as well will be located on SDBS, I'm pretty sure. So now let's look at some example spectra that students have had. We'll start with one that looks sort of nice. So here's one of the student products in the past. Notice how I said plus something extra, because there's obviously something extra than just pure aldehyde. This is Terrence. She had the nice aldehyde peak there down at 10, and as we shift this way, you can clearly see she's got pretty, well, this is very pure butanal product. These 3 peaks match almost exactly the pure product. See how flat this baseline is. So go back to hers. What do we have? You can see that there's sort of a broad little hump there, which is likely to be a little bit of water. And see that little tiny sharp spike? That might be a small amount of the alcohol, might be. But this student's one turned out pretty good and pretty pure. So let's look at another one, which is very typical. Wow. We've got the aldehyde peak, and then we shift down here and it's like, whoa. So clearly this signal, triplet at 2.6-ish, that is one of the CH2s of the product. But then look at right here, right on 4, right at 4. And then you have another triplet and another triplet. And then you have this singlet, this very, very, very tall singlet at 3.5-ish. That signal right there is almost for sure water. Some people can have this tall water peak a little more left or right, but it's normally past 3. That's the signature of water. This peak is right on 4. Can it be starting material in this student's case? And the answer is no, provided that peak of the aldehyde, let's double check that, the pure stuff had the aldehyde peak 9.7-ish. Ah, interesting, not to confuse you folks, but if this happens to you, this student set their reference peak at 10.2. So obviously, this student should have set this one so that peak is a little further this way, which means that peak should be shifted a little further this way. So that peak right there is the alcohol starting material. But they did not quite do their peak picking correctly. And in fact, if we had TMS, and lo and behold, see that little TMS peak? It's supposed to be 0. This student set it at 0.465. So obviously, this is shifted this way a bit much. So when you recorrect it, you can see clear as day that will be the starting material, alcohol. And then these are the 2 other mystery types of products. In this case, 2 more. Don't know what they are for sure, but we definitely know there is something there, which is kind of interesting in itself. So folks, that handles the proton and the IRs.